Okay, well, I'd like to thank the organizers for inviting me to talk. I'm traveling, so I have to give this lecture a la Zoom and just talk directly, show you the slides, but not have any direct contact with you. So it's just being recorded, and I will send this to the organizers. I don't have a great deal of time, and this is a very specific subject with a lot of calculations. So I will just show you the equations and what the final solutions of these things are and what the physics is, but I cannot go into too much detail. Okay, so we'll see what happens from here. So in any case, I want to discuss line bundle hidden sectors. This is generically true, but I'm going to apply it to the so-called B-L MSSM, which is the theory I will describe. It comes from heterotic M theory and is physically quite realistic. And then at the last part of the talk, I will discuss Gaugino condensation and spontaneously break n=1 supersymmetry and get soft terms from Gaugino condensation. This is work that was done with Anthony Ashmore, my students Sebastian Dumitru, and myself recently. So to begin, there's heterotic M theory, which was introduced by these people. But there is a particular model of it, which was worked on by these people. It's called the B-L MSSM. And putting it very, very briefly, we have the theory of Horzava-Witten. We have a observable sector, a hidden sector, and then a one-dimensional sector in between. Let's look at the observable sector. We take this whole thing and we compactify it on a Calabi-Yau threefold, and putting it mildly, we look for a long time for a threefold, which would give us good answers for low energy physics. This turned out to be a self-mirror Schoen threefold, quotiented by a Z3 plus Z3 isometry. H11 and H12 are 3, but we will not discuss complex structure here. So only the Kähler moduli and not the complex structure moduli, and it has an intersection number, which is complicated, but because it occurs in almost all equations here, I'm just showing you what it is to begin with. So we want to look at the observable sector of this thing, and I have to choose a holomorphic vector bundle. We were able to find one. It was an SU4 bundle, and it gives very good low energy physics. We find that the particular SU4 bundle that we found was in fact slope stable, and hence n=1 supersymmetric since its slope vanishes in this particular region for this particular projective coordinate system. I'll show you this again later on. It breaks E8 down to spin 10, but then it has a Z3 cross E3 isometry, which when you mod it out, you can get Wilson lines, and those Wilson lines, which we in this talk will turn on simultaneously. Each of them have their own mass scale. We'll take them to be the same. They break the spin 10 down to SU3, SU2 cross U1 of the standard MSSM, but there's also a gauged U1 B-L, which will be eventually spontaneously broken appropriately. And that will account for a violation of R parity. And I won't discuss that in this talk, but it's important to recognize this extra U1 B-L. The low energy spectrum can be computed for this, and it is exactly that of the MSSM. It's got 2 families of quark and leptons, and it's got Higgs and Higgs conjugate superfields, just one pair of those. It has, for each family, a right-handed neutrino chiral supermultiplet. So this is added, if you like, to the MSSM, but it's a standard thing. And there are no vector-like pairs of any kind, no exotic fields of any kind. So it really gives the MSSM standard supersymmetric model in the observable sector. The hidden sector is another story, and we will get a hidden sector and write it for you, but in general, it could be a non-abelian group and a Whitney sum of line bundles and so on. We're not going to have a non-abelian group, and we will have a Whitney sum of two line bundles, a line bundle L and its inverse L star or L minus 1 if you like, and we'll get to that in a minute. Okay. So line bundle can always be written as O of L1, L2, and L3. These things are integers, but they have to satisfy a certain condition, which makes it C3 cross C3 equivariant. And this is the condition it'll satisfy. I'll give a specific example here, and it of course will satisfy this, but in general, it would have to satisfy this. And there will be many examples one could use, but these things will have to be satisfied in order to be Z3 cross Z3 equivariant. Okay, but we have a line bundle, and we have to embed it into E8. Okay, so we're in a hidden sector. There's a hidden sector E8. And we have to find the embedding and the commutant inside of E8. And once we have done that, there is going to be a numerical constant, which we call little a. You find the generator of the U1 embedded into the hidden E8. That will be Q. You square it, you take its E8 trace, take a fourth of it, and you get A. A will be unity in our particular case, but it need not be if you make other choices. Okay, so that will be the embedding we will use. So describe that. We will also have the physical length of the orbifold that we are going to have to deal with. So let me go back one, I kind of missed that. There's a fifth dimension, and the fifth dimension is given by some standard fifth dimension that we put in just with constants pi times rho, but there'll be a modulus associated with that, which tells you how big it is. It has a coordinate x11, but we can write that as z, which we divide by this pi rho. So that runs from 0 to 1, but we'll also have some other coordinate lambda, which we'll discuss in a second, which will also describe things in the fifth dimension. We have 5 branes. We are going to here assume there's a single 5 brane. It's going to be located at a single point z, and that point z can be turned to a single point lambda using this expression. Lambda goes from -0.5 to 0.5. And this lambda, we are going to choose to be 0.49. That is very close to the hidden wall because it simplifies the mathematics. You don't have to put it there. You can put it anywhere you want. And everything that I will discuss will continue to be true. Okay. The 5 brane, however, has a class which describes it. And it is the Poincare dual 2-2 form to the homomorphic curve on which it's wrapped, and we'll call it W, but there's only one of them. So we just have W, and in order to be n=1 supersymmetric, this single 5 brane class will have to be effective, which means that each of its coefficients have to be non-negative, and we will check that as we go. So having discussed this constituents of this observable sector, a little bit about the hidden sector and also the orbifold sector in this P minus L MSSM, there are a whole bunch of constraints that are physical constraints to make this realistic that we have to satisfy. I'll call them the vacuum constraints, then there's dimensional reduction constraints, and then there are, so I'll call them physical constraints on the theory. They're all physical constraints. These are things that you would want in a theory that is going to be realistic, and we're going to satisfy them. So let's start with the vacuum constraints. There are 3 of these. First one is that the bundle on the observable wall, which is an SU4 bundle, must in fact be slope stable in order to satisfy Hermitial Mills equations and be n=1 supersymmetric. I showed you a picture of where in Kähler moduli space that is, but here I'll give you the equations for it. A1 and A2 and A3 are, if you like, one way of writing the Kähler moduli in the theory, and that's what we're going to use. And so you had better be in this region or this region if you want to be slope stable for SU4. we said that we had one fibrane and it has some effective class Wi, and that has to be greater than or equal to 0, each of its components. It's got 1, 2, 3 components, each of them have to be greater than 0. Then we have an observable sector, and we have an SO10 coupling constant, and that would be G1, and we want G1 squared to be positive, and that's this condition. And then on the hidden wall, it'll turn out, as you will see, to be an E7 will be the low energy non-abelian group that's involved. And we want, let me call it G2 squared to be positive as well, of course, since it's squared, and that gives this condition. And I told you what the IJK is. You see it occurs everywhere in these things. So I've told you what it is. I told you what little a is. I told you what Wi is. So we know all this stuff. So let's get solution to these constraints. Well, SU4 had this slope stability constraint. I showed you one particular form of Kähler moduli space, and showed you this pink region where it was in fact slope stable. Here's another way of writing it. We have A1, A2, and A3, and if we restrict ourselves where each AI goes between 0 and 10, then this is that region in which the SU4 observable sector bundle will be slope stable, okay? Okay, but we have the anomaly conditions 2, and we also have 3 that we have to satisfy. So we have to choose a line bundle in order to do that. L, of course, is going to be O of L1, L2, and L3, which satisfied the condition that it be Z3 cross Z3 equivariant. And then there was a coefficient, which actually has a T at the end of it, which is given by this particular expression. So in order to do this and make sense, we'll take a simple example. We're going to choose in this talk L to be 2, 1, and 3. There are many other choices that one can make, and in our papers you will find all of these things, but this is the particular choice I will discuss here, okay? And when given this, it still has many embeddings that it can have into the hidden sector E8. But here we're going to do the following. We recognize that's a maximal there is a maximal subgroup SU2 cross E7 of E8. And with respect to this maximal subgroup, the 248 representation of E8 decomposes like this. We're going to take the U1 structure group of the line bundle L, and we're going to embed it into the SU2 as 1 minus 1. So the SU2 breaks to U1, and the 2 will turn into a 1 plus a minus 1. And if you work it all out under U1 cross E7, the 248 will decompose in this way. From this, I can read off what the generator Q is. I can square it. I can take it to E8 trace, and I find out that the coefficient A is equal to 1. So it's as simple as possible. And clearly, the low energy gauge group here is going to be, as I said, from here, you embed into SU2, you're going to get an E7. You also get a U1, and the U1 commutes with itself, so it enters the low energy thing as well, but that makes it an anomalous U1. I won't go into this study or talk about anomalous U1s here, other than to mention that there is an extra U1 at low energy here. The gauge connection associated with this will become heavy, but there still will be a charge associated with this U1 for any low energy physics. Okay, anyway, that's our low energy gauge group. To appropriately embed this line bundle L, it's not just simply a line bundle L. We have to actually embed it, and to embed it into E8, we have to extend it to an induced rank 2 bundle, which is L plus L inverse. So that is actually the hidden sector bundle that we have. Okay. And for that particular bundle, the remaining 2 constraints become the following. The anomaly constraint simply turns into Wi is 9, 17, 0. And in fact, there is non-negative. So this thing is effective, and that's completely fine. Okay, so that's satisfied. Again, remember, we have chosen what L is. It's 2, 1, 3. Then what about the positive unified gauge constants here? Well, if we write them out, we get this for G1 squared, for G2 squared, we get this. But as I said, for simplicity, we're going to take lambda to be near the hidden sector brane, and that's a 0.49. So it's just a choice. You don't have to do it, but everything we do henceforth will be that. So if you look for a region in A1, A2, A3 space, you'll find that G1 squared and G2 squared are both greater than 0 in this red region. If we take this and we intersect it with the region where the SU4 bundle was slope stable, we find that we end up in this region. And since the anomaly constraint is always satisfied, all the constraints are all satisfied in this region of A1, A2, and A3. Okay, so you can find a region where that's all true. Now, those are the so-called vacuum constraints, but there's a dimensional reduction constraint, which I sort of hinted at before, but there's a fifth dimension, and the size of the fifth dimension is pi rho times r hat, where r hat is the modulus in that direction. And it's a long story, it depends which metric that you're using, but the fact is we want that fifth dimension to have some extent. It should be, the size of it should be bigger than the Calabi-Yau size, the average radius of the Calabi-Yau. And that's given by this particular expression. So this should be greater than 0. The bigger it gets, the more strong coupling it gets, the smaller it gets, the more weak coupling it becomes. We want it to be bigger than 1, and we're dealing with heterotic M theory, which is a, if you wish, strong coupled heterotic string. V, which appears all over the place, is given by this particular set of its dijk times the various Kähler moduli, and little v is just a volume, a fixed volume that we put in by hand. Okay, then in addition to that, we have a physical constraint, which has been discussed many times before, which is that we want to have a unification scale and a unification alpha, which is G1 squared over 4 pi, to be the kind of thing that one would expect in a unified SO10 theory. And we'll choose, for reasons that are discussed in our paper, 1 over 26.46. And the unification scale should be 3.15 times 10 to the 16 GeV. Okay, and we know that this alpha mu is alpha hat gut, so this is some constant, and since we know what real of f is and can compute this at any point in moduli space, we will get a value for alpha gut hat, that constant at any point you choose in moduli space. And given that and what the real f of 2 function is, which is given by this expression, we can compute what the unified value of G2 squared over 4 pi is, and that is something else we're going to use when we find out. So we can always compute G2 at the unification scale in the hidden sector, okay, and the alpha 2 that goes with it. So if we take all that and we put it all together, so when all of these things work, when the SU4 is slope stable, when the anomaly condition holds, when we have positive G1 squareds, and when the fifth dimension is bigger than the fourth dimension, then for this given bundle L, 2, 1, and 3, and for 5 brane located at 0.49, we find that we will get the correct value of alpha mu at 1 over 26 point whatever it is. I can't read it there, I'm sorry. That is, we satisfy all of our constraints in this brown region, okay? So that's the region of moduli space, A1, A2, and A3, and for any moduli in here, all of the constraints that I just discussed are completely solved. Okay, so we've solved all the fundamental constraints of the B minus L and SSM, but we now have to go back to the hidden sector and really construct it and find a hidden sector that's slope stable and n equals 1 supersymmetric. Up until now, we haven't had to do that. We just simply said what the line bundle we were going to use was, but now we have to show that, in fact, the L plus L inverse is slope stable and supersymmetric and so on and so on. So let's do that. So here's our hidden sector bundle, and that's what the L is that we've chosen. We're interested in preserving supersymmetry, so we look at the phi Laplace term of the D term associated with the SU2, because this bundle has an SU2 structure group, so the phi Laplace term can be worked out and is given by this. It has a piece, which is the tree level piece, but then it has a correction to the genus 1 correction to it. This is actually of order kappa 11 to the 4/3 when we get up to this extra piece here. So from this, one can read off the genus 1 corrected slope, and it's just given by this. That's the inside here. And we're looking at a bundle that is a Whitney sum of L plus L inverse, and that will be polystable and satisfy the Hermitian-Yang-Mills equations if and only if the slope, the genus 1 corrected slope of this vanishes, and therefore this particular guy has to vanish. So we look in Kähler moduli space in 1A2 and A3 for the surface in which we find that the slope vanishes, and hence that L plus L minus 1 is polystable, and hence this thing satisfies the Hermitian-Yang-Mills equations. So there it is. However, having found that, we want to intersect it with that brown region. So I'm just showing a piece of it here that we discussed before, because the brown region satisfies all possible constraints that we need for physics to make sense for us. So this intersection region we call the magenta region. It solves any Kähler modulus in this region, moduli, A1, A2, A3, solves all required vacuum, dimensional, and physical constraints with this hidden sector rank 2 bundle, and that bundle satisfies the Hermitian-Yang-Mills equations, and then it's n equal 1 supersymmetric. So this magenta region we want to focus on, and we will henceforth. So having found the hidden sector bundle satisfying all of the mathematical and physical requirements that we need, we can now compute its low energy spectrum. And there's a long story behind this, but this was done by these people relatively recently using the Euler characteristic, and we find the following Euler characteristic chi for the particular cohomology associated with our U1 cross E7. But the bottom line is that under the decomposition of E8 under U1 cross E7, we get the following thing, which corresponds to one vector supermultiplet transforming into adjoint representation of E7. That's this 133 guy. Then there is one U1 adjoint representation in vector supermultiplet representation, and that's this 1 times 0, 1. Then we get 8 chiral supermultiplets that transform as 56 under E7, but don't have a U1 charge. That's these guys. And then we get 58 chiral supermultiplets that don't transform under E7, but do transform under the U1 with a charge +2. And that's these guys over here. Okay. Having said that, that's our vacuum, and we want to discuss Gaugino condensation in this context. So again, we had the single line bundle, we embedded it into SU2 of SU2 cross E7 inside of E8, and we did that by taking L plus L inverse and so on and so on. Gaugino condensation superpotential is well known. It depends on the dilaton and on the Kähler moduli. We've been using little ai as the Kähler moduli, but if you multiply them appropriately, we'll see it as we move along here. You can also call them capital TI, and H11 was 3, so there are 3 of these Kähler moduli. This is the complex scalar moduli, the A1, A2, and A3 were the real part thereof, or part of the real part. It's well known that when you have an abelian, non-abelian group, which is E7, it becomes strong coupling. The Gauginos can condense and they will produce a superpotential, and this is the form of the superpotential. Note it depends on the unification scale, but also on B of L, which is something that is a coefficient of the renormalization group equation for the E7 coefficient, which we'll discuss in a minute. This alpha gut hat is this constant that we can compute if we pick a point in Kähler moduli space. F2 is given by this expression, but I won't use it here. The real part of T is called little t of I, but that's related directly to A of I. So these are the guys we've been using for the Kähler moduli, and you can get them back to be the real part of T of I multiplying by R hat over V to the 1/3. But the little AI is really the way to go here. And S depends on this volume modulus V. It also depends on the 5 brane through its effective class, and lambda, which as I said is 0.49. Epsilon S prime is a strong coupling parameter, which goes as capital 11 to the 2/3 power. We're always working at this particular unification scale. But B of L, which we have to calculate, depends on the low energy spectrum of the hidden sector. So what is a condensation scale and B of L and so on? So the renormalization group equation for G, I'm taking the inverse, but alpha 2 is G2 squared over 4 pi. And any arbitrary momentum, it's related to the value at the unification scale minus this particular term, and BL enters here, okay? In order for this to condense, BL will have to be bigger than 0, and we'll get to that in a minute. If condensation takes place when P is equal to some lambda, so lambda will be the condensation scale, then in fact, that we can more or less approximate where lambda will be, where this thing will vanish. It becomes very strong coupling, and since it's the inverse, the G is down squared and downstairs, and that would vanish, which then gives us an equation for the condensation scale lambda, which is given by this, which can then be expressed, if you like, in this particular form. So there's enough stuff around. We know what real F1 and real F2 are. B of L we're going to have to figure out. In any case, W can now be expressed in the following form with the lambda cubed out in front of it. Now, supersymmetry is broken here through the S and T I fields and is transmitted over gravitationally to the observable sector, and therefore the scale of SUSY breaking there is actually going to be lambda cubed coming from here divided by m Planck squared, because capital 4 squared is 8 pi over m Planck squared, dimension 1. So m SUSY is this particular quantity, where lambda is the condensation scale, which we can compute from this. Okay. So let's take back to our explicit example, which right now it's been generic, but I'm going to take L to be 213 and alpha U at unification in the observable sector is 1 over 26.46. We know what real part of F1 and F2 are. V is given by this expression. If I expand out in DIJK, we're taking lambda to be at 0.49. And if we plot this thing, we have to find out what what scale, what m SUSY scale is going to be. And let me just say, because I probably didn't say it, because it got lost somewhere here. Okay, well, I don't have time, but let me just point out that for this particular choice of low energy models, one can work out what B of L is. I'm sorry, I've dropped this somewhere along the line. I'm not entirely sure where. And B of L is equal to 6. Don't know where it is. But in any case, we find that B of L is equal to 6 when we have that particular large scale. It's bigger than 0, so therefore you can get condensation. So given that, we take all of this, we plug it into the previous formulas for M SUSY with lambda cubed and Planck squared, and we plot it here. This is that magenta viable region. It goes as A1, A2, and A3. And when we plot it here, you see what M SUSY is. We have M SUSY plotted along the side, and that we see within a certain region, we go between 10 squared and 10 to the 4th GeV. Then in this darker brown region between 10 to the 4th and 10 to the 6th GeV, et cetera, all the way up to 10 to the 12th GeV and beyond, okay? So this is the kind of thing one is going to see in the magenta region, but there's a region down here where you could get very nice supersymmetry breaking, soft supersymmetry breaking scales, and we'll discuss that in a minute. Okay. So what are the soft supersymmetry breaking terms that are related to this? I'm using the work of these people and also Kaplanowski and Louis, but there are many other people involved. I just don't have the time here. We're going to look at the F terms that we get from this gauge condensate superpotential, and I'll just give you the formula here. It's got a Kähler potential linear which breaks into two pieces, a Ks and a Kt piece given by these. Wi is, as I said before, given by that. It's always greater than 0. In the B minus L MSSM, this is the superpotential written in our usual fields. We take all of this as occurring up the unification scale. But following particularly Kaplanowski, Louis, and other papers on this, we will rewrite this in this form. So there'll be a mu hat ij coefficient and a lambda hat ijk coefficient involved in this. The Ci are chiral superfields associated with top and bottom quarks, the tau lepton and up and down Higgs particles. So we're only dealing with the heavier particles, and we're just dropping the rest for simplicity. Okay, so this muij is symmetric and all the terms vanish except for those having to do with the Higgs up and the Higgs down. I'm going to call that mu. This Yij hat coefficient is completely symmetric. It's proportional to the value of the Yukawa couplings raised up to, with the normalization group, the unification scale. And then it has this constant in front, this alpha gut hat, which again changes as we move around in the magenta region. Okay. You also had soft supersymmetry breaking terms in the B minus L MSSM, and here's the whole form of these things. And following what we did above, we'll rewrite that in the following form. So we're going to have mass terms for gauginos. So there are 4 different gauge fields, there are 4 different types of gauginos. We have qubit terms with coefficient aijk, and we'll have quadratic terms with a bijk term. And then we have a mass term here, which goes as C and C twiddle. The lambda are the gauginos for all of the gauge groups. The Ci twiddle are scalar components of the chiral superfields for top and bottom quarks, tau, leptons, and up and down Higgs particles, et cetera, et cetera. See our papers for details. The various soft supersymmetry breaking terms have been worked out in various places. With Lucas and Waldron, we extended them to next order. So it goes to kappa 11 to the 4/3, which had not been done before. And that's what I'm using here. The gravitino mass is given by that expression. So we know what K hat is, we know what W is. The gaugino masses we find are universal, so they're all the same for all 4 gauge groups, and it's given by m1/2, where m1/2 is given by this object, so it depends where we are. Kähler moduli space, lambda is 0.49, and we have to compute over all of these Fs, and that's easy to do, and we did it, and I don't have time to express it here. Please see our paper. The Yukawa couplings, SAIJK, can be written out as some factor A, depends on the moduli, times Yijk. These are the outcomes with the unification scale, and this A is a specific function here given by this. This weird X thing is another weird function given by this. It's a long calculation. I don't have time. The scalar masses have a term which is really complicated, okay? And so we know what all this stuff is, and we can compute all of these like the MAB for an epsilon S prime scale and so on. But I don't have time to do that here. But that thing multiplies a matrix Gij bar, and the Gij bar, we don't know how to compute. It's there is a way, but see the future. I don't have time to discuss it here. It has to be done numerically. It's a difficult thing. But what we're going to do is assume, as people do, that it's diagonal, but also flavor changing neutral currents. Low energy experiments restricted to be not only diagonal, but of a certain form. And this is the form we're going to use for it. So different quarks related certain ways and so on and so on. But we don't know what these values are. So we're going to statistically throw each one of these individually in the range between 1/10 and 10. So there's a huge calculational issue, but we will do that. There's another final parameter we don't know, which is tan beta. We'll throw that at random as well between 1.2 and 65, which are going to have values. One more thing before I give the final answer. Down at 100 GeV at the electroweak scale, we want to get the correct W and Z mass, and this is the mu problem. And it turns out that when you're doing Gaugino condensation, you get two equations that you have to satisfy, one involving mu and one involving B. This is just more standard thing. This is comes from Gaugino condensation. It doesn't matter. What is true is that when you go back to the unification scale, you can compute B over mu, and it's got to be given by a particular function. That function is given by that. And we will see that when you do this, you don't always satisfy this, but sometimes you do, and we'll be very clear about that in a moment. Okay, what kind of results do we get with all of this in Gaugino condensation? Let's choose a particular point in the magenta viable region of Kähler moduli space. We take this particular point, and if we do that, we get the following amazing thing. We're at a fixed point in moduli space, but we throw the Gij and tan beta statistically. This is the mess that we get, okay? And I won't try to describe this. You'll have to look at our papers as to exactly what the labels, the axes here, but they are coming from the various soft terms that we are computing. We are fixing this point, and what we're getting, every point that we find here, when run down with the normalization group, gives all acceptable values. Get the right Higgs value, the correct W and Z mass, all of the supersymmetric particles are above their present bounds, and so on. So it's really fairly remarkable. We did 10 million throws, and we found the total number of points that satisfied those. There were 3,330 such points. Okay, but not all of them satisfied the B over mu value when you scale back to high scale. Those that did satisfy it, we right here in black. I'm sorry, we do here in red. These are the acceptable black points, or they're the red points. The red points are the acceptable black points in that they have the correct value of B over mu at the unification scale. The remaining points, which is most of them, 2,974 of them, also give perfect low energy physics, but when you scale them back, the ratio of B over mu does not have the right value. And so therefore, from that point of view, the mu problem, if you wish, they are not fully acceptable. They're unacceptable, but there are plenty of acceptable ones here too. So as the final slide here, I'll give the full scan. Here's the magenta region again. In this green region, we always find points at any point that we choose here. And we do these statistical throws, we'll always find lots and lots of black points. However, we don't find any red points anywhere except in this particular strip. In this particular particular strip, we find that we get acceptable black points. We get very beautiful red points that satisfy not only low energy criteria, but also this red point criteria, meaning that it's correctly associated with the W and Z mass coming out correctly when you run it back to high energy. So that's very important that we get such points. And, you know, we see where they lie here. They lie down in here, okay? So let me just read it. Magenta region, viable regional space for this particular line bundle. The RGE produces black points for A1, A2, and A3 are sampled at any point in the green region, we can get black points. With the red points, we show in the green space, we find at least one acceptable black point, that is a red point. The region of possible acceptable black points form a strip, that's that red strip that you see. The blue cross indicates this point that we looked at just before. So that's that little blue point here, and it sits right in the middle of that thing. Okay. Now in B, we showed this before. This is the values of M SUSY, and we see that the region that we have this strip band lies right in here. And so we're between 100 and 10 to the 4th GeV, so we get really good low energy supersymmetry breaking scale. So plotted the variation of M SUSY across the viable region, and the blue cross indicates, again, this particular point, and we see that it is between 100 and 10 to the 4th GeV. And the purple line, actually, that goes through here just represents where we're at 1 TeV in soft supersymmetry breaking. So we get very good physical results. So I'm going to stop at this point. I'm sorry that I had to give a talk in this way and I had to move so quickly. It is in our recent papers, but it really would appear that this P-L MSSM, not only does it give very good low energy physics, but you can actually break supersymmetry very nicely with Gaugino condensation, and you'll get great low energy physics, and you also get something that it's not a solution of the mu problem, but it is compatible with Gaugino condensation and the mu problem, which was not easy to accept. So I will leave it at that. Have a wonderful conference and take care. Goodbye.